Today, we're taking a deep dive into something, well, incredibly foundational, the very soil beneath your feet, and how human activity is literally reshaping it.
It really is.
We're unpacking a massive global study here, a real shortcut, I think, to being well-informed on this vital topic.
Definitely. This Kim et al. Synthesis from 2023, it's huge. Over 1,000 data sets.
Gives us a much clearer picture of land use change and its often hidden impact.
And we often focus on, soil organic carbon, SOC, and total nitrogen, TN, total phosphorus, TP. They're absolutely vital.
Right.
What this study really drives home is how fast our land use can knock the balance of these elements, well, completely off key.
Off key, I like that.
Yeah. SOC is key for soil structure. It's a massive carbon store. Nitrogen and phosphorus, they often limit how well plants can grow.
Sure.
But it's the balance, the ratios between them, that stoichiometry, that's like the conductor's score for the whole ecosystem orchestra.
Oh.
And when that score is wrong, it signals problems. Fertility issues, decomposition rates, what's holding back growth, it throws everything off.
So what does this all mean for us practically? Our mission today is to uncover the surprising facts, understand what's driving these changes, and really explore the implications for how we manage our land. Let's unpack this. Okay, let's start with the big ones, the conversions we often hear about. Forests becoming farmlands.
Yeah.
What does that do to these critical soil elements? The study seems pretty blunt here.
It is. Converting forest to cropland, you see a huge drop in SOC, about 33% on average. And total nitrogen down by almost 28%.
Wow. Imagine losing a third of that vital carbon and over a quarter of the nitrogen. That's huge for life support.
It is. But here's the twist, as you mentioned.
Yeah, the phosphorus.
Exactly. Total phosphorus increases significantly by about 10, almost 11%.
Which feels counterintuitive, right? You'd think everything good just drains away.
Right. It makes you ask, okay, carbon and nitrogen are tanking. Why is phosphorus going up?
So what's the answer?
The data points pretty clearly to fertilizer. That's the main driver.
Ah, okay.
You lose the carbon and nitrogen inputs because, well, you're harvesting crops. There's less leaf litter, less ground cover. Plus, tilling the soil really speeds up decomposition.
Right, stirs things up.
But the phosphorus, that increase comes mainly from us adding P fertilizers, often year after year in many farming systems.
And the soil holds on to it.
It can, yeah. It binds to minerals. And interestingly, for this forest to cropland switch, the soil seems to find a new equilibrium, a new steady state for these elements pretty fast.
Oh, fast.
Within about 10 years, typically. So it's a rapid shift in that elemental balance, and that totally changes how nutrients cycle.
Okay, that makes sense with the fertilizer angle. What about forest to grassland? Seems less drastic on the surface.
It does seem less big, and the impacts are different. You actually see slight increases in SOC, maybe around 5 or 6%.
An increase, okay.
Yeah. And nitrogen goes up a bit more, maybe 15, 16%. Phosphorus also sees a jump, similar to nitrogen, around 15%.
But the balance, the ratios.
That's the key difference here. The CN, CP, and P ratios, they don't change significantly. The elements increase, but sort of in proportion, so the balance stays roughly the same.
Interesting. So different conversions, different stories. Now let's flip the script. We've talked about losses. What about gains? What happens when we try to restore things, bring forests back to farmland?
This is where you see some really dramatic results. Reforesting cropland. Well, the SOC increases are huge.
How huge?
We're talking an average increase of 193%, and total nitrogen up by 102%.
Whoa, wait. SUC almost triples.
Almost triples, yeah. Nitrogen more than doubles.
Yeah.
These aren't small bumps. It's like the soil is actively rebuilding its stores over time.
A carbon explosion, you called it?
Pretty much. And what's really key here is that these gains, unlike the quick losses in the other direction, seem to be continuous, meaning they don't seem to hit a ceiling or saturate, even after 100 years of forest growth.
100 years?
Yeah. The data suggests the accumulation keeps going. So if you connect that to the bigger picture, like carbon sequestration for climate change.
It's a very long-term investment payoff.
Exactly. A profound long-term benefit. But again, phosphorus tells a different story.
It goes down here.
It goes down significantly, a decrease of nearly 40% when you reforest cropland.
Okay. So C and N go way up, P goes way down. What does that do to the ratios, the stoichiometry?
It blows them wide open. The CN ratio increases, but the CP and NP ratios increase massively. We're talking CP up by over 400%, NP up by 250%.
So the story there is
Carbon and nitrogen are piling up much, much faster than phosphorus. This suggests that phosphorus availability might actually become a bottleneck, a limiting factor for future growth in these new forests down the line.
Fascinating trade-off. Now, what about turning grassland into forest? Another type of restoration.
That one had a surprising result in this synthesis.
So,
The SOC, the soil carbon, it barely changed. No significant increase or decrease on average.
really, after planting trees on grassland.
Yeah. But nitrogen decreased by about 17% and phosphorus dropped quite a bit, almost 50%.
So C stays flat, N and P drop, but the ratios.
The ratios still went up. CN, CP, and NP all increased, mostly because the N and P decreased while C held steady.
Okay, that is surprising for the carbon. But before we move off forest, you mentioned something. There's a really interesting detail about the type of forest, right? This is where it gets fascinating.
It absolutely is. Forest type matters a lot. It significantly affected the results for SOC, TN, and TP when cropland was reforested.
How significantly?
Okay, get this. Deciduous trees,
Mm-hmm.
like oaks, maples, the ones that drop their leaves,
Sure.
they enhanced SOC storage by almost 30% more than the average reforestation. Nitrogen was up 22% more, phosphorus 14% more.
Better than average, okay.
But conifers, pines, spruces,
In evergreen.
yeah, they actually reduced SOC compared to the original cropland state, down 27%, nitrogen down 35%, phosphorus down almost 7%.
Reduced. So planting conifers on old farmland lost soil carbon.
On average, in the mineral soil measured in these studies, yes, that's a huge swing compared to deciduous trees.
That really makes you pause. It raises a big question, doesn't it, about reforestation projects?
It certainly does. Are we always planting the right trees for the job? Especially if, say, maximizing soil carbon is a primary goal.
So why the difference? Why are conifers performing, well, so much worse for soil carbon in this context?
There are likely a few reasons. First, woody biomass in general has a higher CN ratio than, say, grasses or crops.
Mm-hmm.
Conifer needles also break down much more slowly than deciduous leaves.
Okay.
So you get this buildup of litter on the surface, which is carbon, but it wasn't always included in the mineral soil measurements this study compiled.
A measurement issue, potentially?
Potentially part of it. Also, conifer plantations often lack nitrogen-fixing plants, like legumes that you might find in mixed forests or might be added. And they usually don't get fertilizer. So nutrient cycling is just different.
Right. A lot to consider there beyond just plant trees. Ooh. Okay, one more conversion. Shifts between non-forest types, specifically grassland to cropland. How does that compare?
That's another one with a big impact. Converting grassland to cropland leads to large drops in SOC, about 31%, and nitrogen down 26%.
Wow, that's almost identical to the forest to cropland numbers for CNN loss.
Numerically, yes. It's just as significant an impact. Phosphorus changes were only slight in this conversion, though.
So it's not just deforestation we need to worry about for soil carbon. Plowing up grasslands is a major issue, too.
Absolutely. It's easy to overlook, but grasslands store a lot of carbon, especially below ground.
Why is the impact so large there?
Well, think about grasslands. They often have plants with really dense, deep root systems. That's a constant input of carbon deep into the soil.
Mm-hmm.
They also tend to have green cover for more of the year, fixing more carbon overall compared to many annual crops.
Yeah.
Then you bring in the plow.
Cultivation.
Yeah. Repeated cultivation. It stimulates decomposition, breaks up soil aggregates that protect organic matter, and just makes the soil way more vulnerable to erosion. You lose that protective shield.
Okay, so we've seen these individual changes. What about the bigger picture? Are there overarching relationships when you look across all these land use shifts?
Yes, definitely. One really strong pattern is the link between soil, organic carbon, and total nitrogen.
They move together.
Very closely, yeah.
Oh.
Across most land use changes, the changes in SOC and TN showed a strong linear correlation, often almost one-to-one, like they're joined at the hip, as you said earlier.
Mostly. But you mentioned an exception.
The main exception was after forestation, especially on cropland. In those cases, the big SOC increases sometimes outpaced the nitrogen increases. Carbon really took off, sometimes doubling the N increase.
Carbon sprints ahead when forests return. Got it. What about phosphorus? Does it march to its own beat?
It really does seem to. As we discussed, changes in TP were positively correlated with phosphorus fertilizer application rates. A reasonably strong link there.
Makes sense.
But, crucially, TP changes weren't consistently correlated with the changes in carbon or nitrogen.
So fertilizer drives P, but C and N move more with the organic matter itself.
That's what it suggests. Phosphorus isn't always tied up in that organic framework in the same way. It can stick to soil minerals, hang around longer, especially when we add it externally.
And the ratios reflect that.
They do. The CP and NP ratios showed much, much wider swings after land use change compared to the CN ratio, which was generally more stable. It reinforces this idea that P dynamics are somewhat independent.
Okay. And what about climate? Temperature, rainfall, surely they play a big role.
You'd think so, and they do have some influence, but the picture was, let's say, nuanced in this big synthesis.
Not a clear-cut driver across the board.
Not really. There were some correlations with temperature. For instance, higher temperatures seemed linked to greater losses of C, N, and P when forests were converted to cropland or grassland.
Okay, warming makes those losses worse.
And conversely, warming was linked to slightly less C and N loss when grassland went to cropland. But overall, the study concluded that few generalities emerged for climate as a dominant controlling factor across all these changes.
Any other climate surprises?
Well, there was one interesting point about precipitation and converting grassland to forest. Previous studies, smaller ones, suggested that higher rainfall led to smaller SOC increases, a negative correlation.
More rain, less carbon gain. Why?
The thinking was maybe faster decomposition or leaching in wetter climates. But this new, much larger data set, crucially including sites with very high rainfall,
What did it find?
it found the opposite, actually a slight positive correlation, meaning, if anything, more rain might slightly favor SOC gain in those situations, or at least there's no important interaction.
So the bigger data set overturned the previous finding.
It seems so. It really highlights the power of these large syntheses, bringing in more data points from diverse conditions to refine our understanding. What stands out to you about that kind of shift in understanding?
It tells me we constantly need to update our models and assumptions as we get more comprehensive data. What seemed true locally or regionally might not hold globally.
Precisely.
Okay, this is incredibly insightful. Let's bring it home. Let's unpack the actionable insights for you, the listener. How can we use this knowledge to manage land better for soil health, for climate goals?
Right, the practical side. Well, the research offers some clear directions. First, where forest conversion to agriculture might still happen.
Which it unfortunately does.
Yeah. Strategies like agroforestry, integrating trees with crops, or livestock and conservation agriculture practices can make a real difference.
Like what kind of practices?
Things like keeping the soil covered with cover crops, reducing tillage, applying organic amendments like biochar or manure or compost. These can really help mitigate those big SOC and TN losses we talked about. They can cushion the blow.
So, soften the landing when forests are cleared. What about the other way? Optimizing forestation.
Absolutely. If maximizing soil carbon storage is a goal, the study strongly suggests favoring non-coniferous species.
Like the deciduous trees we discussed.
Exactly.
Sure.
Oaks, maples, those types. And importantly, consider mixed species plantations, especially including nitrogen-fixing legumes.
Vital legumes.
They pull nitrogen from the air, enriching the soil. This helps prevent nitrogen from becoming a limiting factor, potentially allowing for greater overall growth and carbon uptake. In fact, mixed plantations globally tend to be more productive, about 18% higher biomass on average than single-species stands.
So diversity is key there, too.
It often is in ecosystems.
Yeah.
But there's a really crucial caveat to all this.
Which is?
While these global averages give us a powerful overview, the study also showed huge variability from site to site. The outcomes aren't uniform everywhere.
Right, local conditions matter.
Tremendously.
Yeah.
So what really stands out is the critical need for, well, location-specific assessments. We need local studies and continuous monitoring of soil carbon, especially in reforestation or restoration projects.
To make sure the intended benefits are actually happening on the ground.
Exactly. We need to verify. Global averages are a starting point, but effective management has to be tailored to the local context.
That makes perfect sense. Wow, we've covered a lot of ground, literally. We've journeyed through these huge global data sets, uncovered some really surprising connections, and I think identified key drivers of soil health during land use change.
Yeah.
It's just so clear that our decisions about land use have these profound, really long-lasting impacts on the vital elements right beneath our feet.
Absolutely. And despite how comprehensive this synthesis is, there are still fascinating unknowns, things we need to dig into more.
Oh, like what?
Well, think about deep soil layers. Most studies focus on the topsoil, maybe the top 30 centimeters.
Oh.
What's happening deeper down? And what about the carbon locked up in, say, large, dead tree roots?
Or coarse roots.
Yeah, they often get sieved out or discarded in soil sampling, but they can represent an immense, very long-term carbon pool. How does that change when land use shifts? We don't fully account for it yet.
So more layers to uncover, both literally and figuratively.
Exactly. This deep dive really shows us how complex, how dynamic, and just how vital the ground beneath us truly is, and how much more there still is to learn.
A great place to leave it. Keep digging, keep learning, and join us next time for another deep dive.